This is the fourth video in the chapter on organometallic compounds. And it's a little bit different in that this is going to involve reactions that don't seem to be involving organometallic compounds at all, but we will see when we get into the mechanisms that they actually do. But before we start that, let's talk about the fact that this is going to be two new reactions very similar to each other that involve what are called carbenes, and in one case a carbenoid. So what is a carbene? Well, let's review the kinds of intermediates we've seen so far. You all are very familiar with carbocations. Those are carbons that have a positive charge, 3 bonds, and not an octet. So carbocations are generally only seen in mechanisms where they're formed and then formed very briefly and then used up again in the next step in a mechanism. So no octet there. The other kind we've seen is free radicals, one particular kind of reaction called free radical halogenation. And free radicals are carbons, again, they have 3 bonds to them, but instead of having 0 electrons as carbocations do, they actually have 1 unpaired electron on that carbon. And because they have 1 more electron, they don't have a positive charge. They have a valence of 4. 1, 2, 3, 4. So it's a neutral molecule, but does not have an octet and has an unpaired electron, so it's very unstable. Again, free radicals only occur in mechanisms where they'll be formed and then immediately used up again. We've also seen carbanions. Carbanions are carbons that have, again, 3 bonds, but this time 2 to make up a lone pair on that carbon, and because they have an extra electron that the radical doesn't have, they are then negative. So carbanions have a negative charge, and notice that carbanions do have an octet, and so carbanions are actually more stable than carbocations. In fact, a few carbanions are stable enough that you can keep them in solution, or maybe even in a solid state in some cases. We have seen, for example, acetylides that are actually compounds that you can use in a synthesis. But now we get to a fourth kind that we haven't seen before, and this is a very odd-looking thing. It's a carbon with only 2 bonds to it and a lone pair, so it seems like it shouldn't even exist because it just looks so unusual. But the fact is, notice that it has a valence of 1, 2, 3, 4, which is what it should have, and so it's a neutral molecule, not charged, so not positive or negative, but neutral, sort of like a free radical. But everything is paired up, which makes it a little bit better than a free radical, but it still does not have an octet. And so that's why carbenes are quite unstable in the sense that no octet. Carbenes generally are not stable molecules, not found in bottles or even in solution for periods of time. Again, they only occur as intermediates in mechanisms. So in terms of the answer, charge 0, octet no. But we will see a mechanism involves a carbene here in a few minutes. Okay, now let's do a little bit more thinking about carbenes and their electronic structure. It turns out there's actually 2 varieties of carbenes. There's this kind that I drew on the previous slide, which has the 2 electrons on the carbon not paired, not bonded to anything, but paired in 1 orbital. This is called singlet carbene. I'll explain why it's called singlet carbene in just a minute. The other way you could imagine it would be 2 bonds and 2 unpaired electrons on that carbon. So sort of like a double free radical. This is called triplet carbene. In singlet carbene, if you look at the groups of carbons, it'd be 1, 2, 3, so therefore trigonal planar, sp2, 120-degree bond angle. In this case, it would be 4 groups of electrons, 1, 2, 3, 4, where a single electron constitutes a group in this case. So that would have 4 orbitals. That would be sp3, 109.5 degrees, tetrahedral for its electron group arrangement. Now notice that if the 2 electrons are paired up, there's only one way they can be spinning with regard to each other, and that's 1 with a +1/2 and 1 with a -1/2, or showing it as a paired set of arrows, 1 up and 1 down. That's the only way they can be, so that's why it's called singlet carbene. But with a triplet, the 2 electrons aren't in the same orbital, so they can have a variety of spins with regard to each other. They could both have a +1/2, they could both have a -1/2, or they could have 1 of each. And so there's literally 3 spin states for a triplet carbene. Both up, both down, or 1 up and 1 down. Because they're not paired, the one doesn't care what the spin of the other one is. Now, let's talk about the 2 reactions in this chapter. The first one we're going to call addition of dichlorocarbene to alkenes. It doesn't have a fancy name. We'll just call it addition of dichlorocarbene to alkenes. Notice that it starts with an alkene, and it adds to the double bond. So this is another reaction of alkenes, another addition reaction that we can now go back into the previous chapter on alkenes and learn about a new way of adding things to the alkene. What we do is we start with the alkene, we add in this molecule, which is a carbon, 1 hydrogen, and 3 chlorines. That thing is called chloroform. I'm sure you've heard of chloroform before. I don't know if you realize that this is what it was, but chloroform is just trichloromethane for its IUPAC name. And it's a very common solvent. It's kind of carcinogenic, but it's used in some cases for various purposes. In this case, it's the reagent. So we're adding in chloroform. We're also adding in a strong base. The one I've shown here is typically used T-butoxide with potassium. In other words, potassium T-butoxide. That's just an alkoxide, which you remember is a carbon group, in this case T-butyl with an O minus, and then in this case potassium is the counterion for that. So this is, again, a very common reagent that you will find on the stockroom shelf in most cases. So we take the alkene, we take chloroform, and we take potassium T-butoxide, we put them together into a flask, and we end up with this very interesting new molecule in which this carbon-carbon double bond has disappeared, but it's now bonded, both carbons bonded to another carbon with 2 chlorines on it. And so it makes a 3-membered ring. These 4 groups on this part of the molecule were these 4 groups on the alkene molecule. In case you're interested in the byproducts, the T-butoxide turns into T-butyl alcohol. That just becomes part of the solvent, essentially. And the potassium and one of the 3 chlorines makes potassium chloride, again, an inorganic ionic compound that is removed from the reaction mixture. The other 2 of these 3 chlorines end up on the bridging carbon here. So this reaction may look kind of familiar. It's sort of like the epoxidation reaction that alkenes undergo with MCPBA. Remember that reaction which makes a 3-membered ring with an oxygen bridge? Well, this is again a 3-membered ring, but now with a carbon bridge. So in essence, we've made 2 new carbon-carbon bonds. Thus I put 2 asterisks here because it's making not 1, but 2 carbon-carbon bonds. Really neat thing to be able to do. So this is one new reaction you'll be learning. Pretty simple. The other new reaction in this chapter looks really similar. Again, it starts with an alkene. It starts with a reagent that has halogens and hydrogens on a carbon, but in this case it's 2 hydrogens and 2 iodines. So this could be called diiodomethane, or it could be called methylene iodide. It's another name for this particular compound, or CH2, sometimes referred to as a methylene group. So you take this material and zinc and the alkene, mix them together in a flask. Also helps if you have some copper metal present, although that's not really part of the equation. And you end up with, again, a 3-membered ring, a single carbon bridging between those 2. But this time, instead of having 2 halogens attached to it, as this does, it's just 2 hydrogens. So this is now a hydrocarbon in which you've made a 3-membered ring from an alkene. The byproduct here is very simple. The zinc metal and the 2 iodines combine together to make zinc iodide, which again is an inorganic ionic compound, and it precipitates out of the reaction mixture. So here are some examples. If we start with this alkene, which happens to have double bond in a ring, so this would be cyclohexene, and we do the dichlorocarbene reaction with chloroform and potassium T-butoxide, then we get the 1 carbon bridge and make this kind of 3-membered ring cap on the 6-membered ring, and the 2 chlorines are there. Almost looks like a Mickey Mouse hat, sort of, where the 2 chlorines are on this 3-membered ring as a hat, sort of. But it works with other alkenes too. So this alkene, we make the 3-membered ring across there with the 2 chlorine. This one illustrates the fact that if the alkene is cis to start with, this is a cis alkene, then those 2 groups end up cis to each other on the 3-membered ring. If they're sort of trans alkene, then the 2 groups would end up trans on the 3-membered ring. And finally, this is a simple case, but it looks complicated because of the format of drawing the structure that I've used here. This is a 3-carbon chain with a double bond and a methyl group on the 2nd carbon. Here's your 3-carbon chain, 1, 2, 3, with a methyl group on the 2nd carbon. This is where the double bond was. Now it has a 3-membered ring with the 2 chlorines attached to it. So these are just examples of how you would do that reaction. Similarly, with the Simmons-Smith reaction, same idea. In each case, we're bridging that carbon-carbon double bond with a 1-carbon piece. In this case, though, because there are no chlorines, it's just a CH2 group, CH2 group, CH2 group, CH2 group. Same reactions in this case. Now, how would you do a synthesis using one of these reactions? Well, what I'd like you to do at this point is take a look at this molecule right here and figure out a way that you would make this from an alkene. So it's pretty simple. You can use any alkene starting material you want to. Pick your alkene starting material, and you're going to want to throw in chloroform and T-butoxide, and that will give you that synthesis. Same thing here, but without the chlorines. So this is obviously going to be the addition of dichlorocarbene. This is going to be the Simmons-Smith reaction. So you have to decide what alkene do you start with here and what alkene do you start with here. Pause the video, and I will answer the question on the next screen. So here we go. If this is your target molecule, then it's that carbon and the two chlorines that we want to bridge across these two carbons. And so you're going to want that to be a carbon-carbon double bond in your starting material. So this alkene looks a little funny because you're used to double bonds in rings, but this is a double bond that's pointing off the ring. It's perfectly okay to have those kinds of alkenes. So this would be your starting material in this case. And then in this case, because we want this ethyl group and this methyl group to be arranged stereochemically to this group, where this methyl and that propyl group are cis to each other, and this ethyl group and that propyl group are trans to each other, we want this methyl group and this propyl group cis to each other on the double bond, and this ethyl group and this propyl group trans to each other on the double bond. And then we just do the Simmons-Smith reaction with this reagent, and you're done. Now, let's talk about mechanisms here for a minute. This is where the organometallic part comes in, because you'll notice up till now, none of the things that we looked at were actually organometallic. There were metals involved, zinc, potassium, but why is this being handled in the organometallic chapter? Well, here's the mechanism of this particular reaction where we're taking chloroform and an alkoxide, that could be T-butoxide or other alkoxides, and we get this product plus these byproducts. The alkene actually doesn't come in the first step of the mechanism. The first step in the mechanism is that the chloroform and the alkoxide combine, and the alkoxide, being a strong base, pulls off that hydrogen, and that gives you this molecule with 3 chlorines on a carbon with a lone pair, which of course is a carbanion. So this is a negative carbon, there's a negative charge, and of course this is simply an acid-base reaction, so this base turns into its conjugate acid, which is the alcohol, and then you have this interesting carbanion with 3 chlorines. Next step, that carbanion with 3 chlorines essentially kicks out ACl minus. So it says, I'm not really happy with having this negative charge on carbon, I'm just going to kick out the chloride. So here's the chloride, and that of course is a very stable thing. Chloride, we see that all the time, and that leaves us then with this molecule. If we take this, which has 3 chlorines and a negative charge, and we take off 1 chlorine and a negative charge, that leaves 2 chlorines and a neutral molecule. This, of course, is a carbene. Notice a carbon with 2 bonds to it and a lone pair. So this is where the carbene thing comes in. We call it dichlorocarbene. Then that, which happens to be singlet carbene, does the reaction with the alkene. And so it forms 2 bonds with the double bond, both at the same time. And because of several things happening there at the same time, let's draw curved arrows for that particular step. And as you know, you can draw curved arrows for any mechanism step. Most of them aren't that interesting, but this one is interesting, so let's go ahead and do that. So notice here's the dichlorocarbene, here's the alkene, the dichlorocarbene sits down on top of it. That pair of electrons comes in and makes a bond with this carbon. That pair of electrons from the double bond goes up in here and makes another bond between that carbon and that carbon. And so both carbon-carbon bonds are made at the same time. Here's the mechanism of the Simmons-Smith reaction. Again, here's the overall reaction. Here's the steps. It's a 2-step mechanism. So the first step, the zinc essentially inserts itself between the carbon and one of the iodines. So there's the CH2. There's one iodine still bonded to the CH2, but then the zinc is in between the carbon and the other iodine. So it's kind of like a Grignard in that sense that magnesium inserts itself into a carbon-halogen bond. Well, here zinc inserts itself between a carbon and a halogen bond. And then that thing, which I've redrawn here, because of course the zinc iodine bond is actually ionic, so you have a positive on the zinc and a negative on the iodine. That thing comes in and attaches to both carbons of the double bond at the same time, and at the same time breaks off the iodine from this side and the zinc from this side. So that's a pretty complicated looking thing. And the net result is that the iodide, the zinc becomes zinc plus 2. This iodide all together forms ZnI2, or zinc iodide, which is the byproduct. But the interesting thing is this organic molecule. So here's the curved arrows. This is the sort of Lewis dot structure type thing for this molecule. Notice here's the CH2. Has an iodine bonded to it covalently, has a zinc bonded to it covalently, and then this other iodide is hanging off there as a negative ion. Well, this bond between the carbon and the zinc moves in here to form a new bond between this carbon and that carbon. At the same time, this double bond from the alkene moves in here to form a new bond between that carbon and the other carbon of the alkene. And at the same time, this pair of electrons between the carbon and the iodine gets kicked out. And so you end up with I minus, you end up with two new bonds to the carbon, and you end up with the other zinc, or the other iodide and the zinc left over. So those two mechanisms, the Simmons-Smith reaction that I've outlined here and the addition of dichlorocarbenes to alkenes, are both reaction mechanisms that you should know. Oh, by the way, one other thing to notice here is there is never a carbene in this particular reaction. This carbon, CH2, that looks like it might be a carbene at some point, is never actually a separate molecule, so that's why this is called a carbenoid reaction. Carbenoid meaning like a carbene, but not actually a carbene. So thank you for your attention.